Hello, everybody, and welcome back. So you should have just watched the lesson on energy and reactions. The ending of the video did end a little bit abruptly, and I apologize for that. It's just because I was running out of time on my recorder. So if you felt like the end was a little bit rushed, sorry, but I am going to go over some of these problems with you right now. These are going to be similar to what you guys are going to do for your independent practice today. So I have linked a sheet that you can open and kind of like type it in as we follow along or as you follow along. But if you don't want to do that, you can always just like watch these to help you and use them as a reference. So let's go ahead and get started. So again, we're going to be looking at energy diagrams today. And if we just remember, this is your the time elapsed as your chemical reaction is taking place. And then here's our heat content in kilojoules, right? So our heat content is on our y-axis, and then our time is on our x. So if we're looking at this, remember, we're going to be looking at things like activation energy, also the energy of our reactants and our products. Now remember, reactants go on the left-hand side of the equation, it's what goes in, and the products go on the right-hand side. Hello, everybody. So welcome back. You should have already watched your lesson video for the day, and I know that the end probably seemed a little bit rushed, and I apologize for that. I was running out of time on my recorder, but it's okay because we are going to go over energy diagrams right now. I'm going to go through some example problems with you, work them for you, and your independent practice problems today are going to be very similar. So if you'll just stay with me, I did link a worksheet that if you wanted to fill it in as we go through these, you can. Or if you just want to watch this to get some practice and then jump headfirst into your graded activity, it's totally fine. It's up to you. But I do recommend watching these before you try to do your independent practice for the day. Okay. So here we have a picture of an energy diagram. So again, this is just showing you kind of what happens during a chemical reaction. So we've got our heat content in kilojoules on our y-axis, and then we've got our time of our reaction on the x. So basically this is showing you what's happening to the energy of your chemical reaction as it's taking place over time. Okay, so this first question asks us what the heat content of the reactants of the forward reaction is in kilojoules. So basically, again, I told you we were going to talk about reverse reactions later on when we talk about equilibrium, but it's asking you to give the initial heat or the initial energy of the reactants. Okay, and if we remember on our energy diagrams, our reactants are going to be here, right? Our products are going to be here, okay? And then our activated complex is going to be up here. So the heat content of the reactants, so what goes into the equation on the left-hand side is right here. Here's the energy of our reactants. And if we follow this line, we see that lines up with 80 kilojoules. So the heat content of the reactants is going to be 80 kilojoules, okay? It doesn't have to be complicated. It's not that complicated. I know a lot of times when you look at a chart and you see something like this, your brain goes fuzzy and you're like, oh, what is this? But if we break it down and we look at it and we take it step by step, you guys should be a-okay. All right, let's look at another one. The heat content of the products of the forward reaction, again, just going left to right, that's what it means by forward reaction. So starting with our reactants on the left and ending with our products on the right. It just wants to know the heat content of just the products. Okay, so again, reactants on the left, products on the right. So if we follow this line over, our heat content or energy, initial energy, or not initial energy, but our energy of our products is going to be 160 kilojoules. Okay, and that's just because here's the energy, here's the line that corresponds with the energy of our products, and that lines up with our 160 kilojoules. Okay, so that means that after this reaction has run its course, let's say it's a 10-minute reaction and it takes 10 minutes. So after 10 minutes, your products have an energy or a heat content of 160 kilojoules. So here it says the heat content of the activated complex of the forward reaction is about what? So again, our activated complex is located right here at the peak. We should have looked at that in that chart in our lesson video. So our activated complex is here. and that corresponds with 240. So it's going to be 240 kilojoules. You really just have to follow the line over and read the corresponding heat content. Okay? And of course, if you guys have any questions about any of this, you can always reach out to me and schedule a tutoring session via Zoom. The activation energy of the forward reaction is blank kilojoules. So it's asking you for the activation energy. And again, we went over this towards the end of our lesson for the day, so in that last video. So your activation energy is the amount of energy it takes to actually make the product, so to get the reaction up and going. So here we have our energy of our reactants, right? And we have to find the difference between the energy of our reactants and how much energy it takes to get to that activated complex, okay? So our activated complex is at 240, and then our heat of our reactants was 80. So we're going to do 240 minus 80 because that's the difference in the energies. And that's going to give us 160. So the activation energy for this complex is 160 kilojoules. We just have to find the difference between your reactants and the energy of the activated complex, because that's how much energy it took to get us from the reactants to that activated complex. Now it's asking for the heat of reaction, so the delta H. Remember, delta stands for change, so the change in the heat of the forward reaction. Now, in order to do this, to find your delta H, you want to look for the change of the energy in the products and in the reactants. So remember, again, this was in that lesson video. So we're going to take the value of the energy of the products on the right-hand side, and we're going to subtract the energy of the reactants on the left-hand side. So remember, we already said that the heat energy of our products was 160 kilojoules. So we will take 160 and we will subtract 80 to give us a total of 80 kilojoules, right? Now this delta H is positive, right? This is a positive delta H. We have the energy of our products higher than the energy of our reactants. So this is going to be our indication, remember, that this is an endothermic reaction, right? So this system is absorbing heat. It's taking heat in. So, oh, that was this question. So the forward reaction is either endothermic or exothermic. It's endothermic. Again, you know that just by looking at this because your products right here are higher in energy than your reactants. Okay, that's the first way to tell. And also you can tell the calculation of your delta H. So remember, we calculated it to be a positive 80 kilojoules. That positive delta H indicates that it's endothermic. So here's a different one. So you were looking at one particular problem earlier. Now let's look at another one. It says the heat content of the reactants of the forward reaction. So again, it's just looking for the heat content of the reactants, which are on the left. Remember, reactants are on the left, products on the right. Here we are at 40 kilojoules, okay? Because your reactants, this line for your reactants are just sitting at 40. Now it wants the heat content of the products. Okay, so reactants on the left, products on the right. And again, these products correspond with about 20 kilojoules. Okay, so we should be getting the hang of it now. The beauty of virtual learning is that you can pause and rewatch as many times as you need to until you get it down. Next one says the heat content of the activated complex of the forward reaction is about, do you guys remember where the activated complex is? Yes, it is right at this peak right here. Okay, so your activated complex is right here. Remember, your activation energy is the difference in the energy of this activated complex and your reactants. Remember, your activation energy is how much energy it takes to actually get the reaction going and to form your products. So here's where our activated complex is, corresponding with 100 kilojoules. Activation energy, so we need to find the difference. Remember, our energy of our reactants was 40. The energy of our activated complex was 100. So 100 minus 40 is going to give us 60 kilojoules. Okay, so again, it can be a little bit intimidating to see charts like this, but once you learn how to read them and break them down, it's basically the same thing over and over. So if you can get the steps down and just remember where your reactants, where your products, and where your activated complex are, the rest is pretty simple. So your enthalpy change, so your delta H of the forward reaction is, so again, here's our products, right? So we need to find the change in our products and our reactants. So our products are at 20 and our reactants are at 40. So 20 kilojoules here, 40 kilojoules here. Now, remember to find your change in enthalpy, so your delta H, you want to do your energy of your products minus your energy of your reactants. So we're going to take 20 and we're going to subtract 40. And then you have to do it this way because remember, it does matter whether or not it's a negative or a positive number. So if we do 20 minus 40, that's going to give us negative 20. So that means the change, the delta H of this reaction is going to be negative 20 kilojoules. So is this endothermic or exothermic? Remember, this is basically the opposite of the first example we did. So here we've got the energy of our reactants actually being higher than our energy of our products. And we've got a delta H that is now negative. A negative delta H and a reaction that has energy that's lower in the products than it is the reactants is going to be an indication of an exothermic reaction. Remember, in an exothermic, exo means out. System is releasing heat. Okay? And that's it. So I did go through those pretty quickly, but it's kind of just almost like a plug and play. So if you have any questions about that, let me know. Send me an email, send me a remind, schedule a Zoom tutoring meeting, whatever you guys need, let me know. Watch this video and your lecture video as many times as you need. You do have an independent practice to do today and submit for a grade. So I hope you guys all have a really great day and I hope to hear from you guys soon. Talk to you later.